Hey guys, Mr. S from Sanitas Academy. Um, Still stuck inside because of COVID-19. Hope you guys are all doing well. I wanted to shoot out a video for some of the older crowd today, as well as some of the high school students who use things like pi, but don't know what they derive from. So we'll do a little bit of geometry and algebra to see how the number for pi came about.
Alrighty, so what you're going to need is a ruler, if you like staying neat, a pencil, and a compass. Nothing crazy. First and foremost, let's just draw a circle so we understand exactly what we're talking about when we say pi. Alright, this is a circle. What pi is a number that when multiplied by the diameter, pi times diameter, will equal the circumference, or the perimeter, which is the length of the entire circle if you have to walk all around this thing over here. Okay? And before we go on, let's at least make sure that we write a name down, because everybody knows who Pythagoras is, but nobody knows who Eratosthenes is. So let's write this down. Eratosthenes. And he is not famous, but is the creator of pi here. Now, whether or not this number existed and was discovered before him, we're not very sure of, but this is the man that we want to make sure we give credit to here. And why is pi important? Pi is important because if you know the length of the circle from one side to the other, then you can easily find the circumference. And it also helps with a lot of other things like finding the area of a circle. For Eratosthenes, this was important because he found the distance from one side of the earth to the other side of the earth and back around, or the circumference of the earth. Okay, so let's try figuring out exactly how to do this when we know nothing. So first and foremost, this circle, we are going to say, will have a diameter of 1. But I won't write that down because I want to focus on it having a radius of 1/2. Because if it has a diameter of 1, it inevitably has a radius of 1/2. And what we are going to do now is we are going to start inscribing shapes. And what Eratosthenes did was he inscribed, if you don't know what the word inscribe means, it means a shape that touches the inside of the circle. And we're of course talking about perfect shapes with equivalent sides. And circumscribe means a shape that has points touching the exterior, which is outside the circle, but touching the exterior or the circumference of the circle. So for example, if I were to inscribe a square within this circle, it would look something like this. Oh, that was ugly. Excuse my insolence. Alrighty, a little bit of that. So right now what we did was we inscribed a square inside of here, okay? And circumscribe would look something like this. The square would be outside of this circle, but would be touching the circle in 4 points. Those 4 points, I made sure, were the exact same points as the square that was inscribing, right? So we have circumscribe on the outside, around, right? Circum means around, and then inscribe within for this square. So what Eratosthenes reasoned was that the perimeter of this interior shape, of this interior square, and the perimeter of the circumscribed square should give us a bit of an idea of what the perimeter of the circle is. The perimeter of the circle should be somewhere between the perimeter of the inscribed square and the perimeter of the circumscribed square. Now, how exact can we be about this? Well, not very exact. The best we can do is create an inequality, right? So the inequality would be something like perimeter of inscribed square is less than perimeter of circle, which is less than perimeter of circumscribed square. But what we want to do is we want to bring this perimeter as close as we can to the perimeter of the circle. We want to bring the circumscribed perimeter as close as we can to the perimeter of the circle. And how can we do that? We can do that by changing the shape. As long as we have a shape with more sides, more points will touch the circle. And inevitably we'll be going closer and closer and closer to understanding what the perimeter of the circle will be. And I'll show you how to do that in a second. So first and foremost, let's do a little bit of geometry here. Let's find out what, and we're going to focus on the inscribed square here, right? Let's find out what the perimeter of this inside square is. Okay, so we have 1/2 right here. And inevitably that also means that we have 1/2 here. Do we care what form of measurement it is? Inches, meters? We don't care. 1/2 right over here. So with Pythagoras, we can use his theorem. We understand that this is a 90-degree angle. So inevitably a squared plus b squared will give us c squared. So we have 1/2 squared plus 1/2 squared, and we would write equals c squared, right? And so I'll write that just to make sure that you guys see it first. But I am not the biggest fan of equations. I think they're overused. Let's make an expression so that we can solve the expression for the perimeter of this square. So the expression would look like, what does c times 4 equal, right? Because this is c, and we have 4 of these. So c times 4. First and foremost, let's see what c equals. For c, we'd have to make sure that we throw a square root sign on both sides over here. So we have square root of 1/2 squared plus 1/2 squared. This equals c. We need 4 of them. So all we do is throw the number 4 in the front, and we have 4 square root 1/2 squared plus 1/2 squared. All right. Now, what does squared mean? Everyone knows what that means. It means the number within this parentheses times itself. So what is 1/2 squared? Well, 1/2 squared is 1/2 times 1/2. So 1/2 squared will equal to 1/4 plus 1/4 on this side as well. Throw them all underneath the square root sign, bring down the 4. We have 4 square root 1/4 plus 1/4. What is 1/4 plus 1/4? It is 1/2. 1/2. So we put that inside of the square root sign again. We have 4 square root 1/2. Now this 4 out here is being multiplied by the square root of 1/2. But we can show it inside of this square root as well. This 4 would be the answer to square root of 16. So we have 4 square root of 1/2 is the same thing as square root of 1/2 times 16, or square root of 1/2 times square root of 16. Then we multiply across, and what we get is square root of 16 over 2. And this can easily be shown as square root of 8. Now we have square root of 8 over here. I'm going to bring this all the way up here. And that square root of 8 I'm going to turn into square root of 8 is equal to, and I'll erase that so you remember what I had down low, 4 times 2, because 8 equals 4 times 2. Now that we have square root of 4 times 2, we have square root of 4 times square root of 2, and we know that square root of 4 is equal to 2. So we have 2 square root of 2. And this is what? This is the perimeter of that inside square. All right, so I went ahead and I redrew the circle that we originally drew, as well as the square inside. I just drew it a little bit larger because we are now going to be moving on to the second step. The second step is to create another shape that is inscribed within the circle, but has more sides and touches the circle more times, which means is going to be closer to the perimeter of the circle. So to do that, we are going to find a center point, by eye, a center point between these 2 points that is on the circle, and we are then going to be drawing lines directly from the corner on the square to that point. Now, this I'm going to show on only one side, but I'd like you to know should be done on all sides. So the shape inevitably would be what? 2 sides instead of 1. So instead of 4 sides, it would have 8 sides. It would be an octagon. So that octagon would be inscribed inside of the circle. And wouldn't you say that this octagon would be much closer to the perimeter of the circle than this square? I would say so too. So now our job is to figure out what the perimeter of this octagon is. So I'm going to go ahead and draw some very important things for us. So we originally said that this circle had a diameter of 1. So the radius was 1/2. That also means that this line from the center point to the edge of the octagon we are drawing should also be 1/2. And I'll make that smaller over there. So from here to here is 1/2. Got that? Okay. Now that we know that that's 1/2, I want to make sure that we take our answer, 2 square root of 2, and we plug it in somehow. But please remember that 2 square root of 2 was actually the perimeter of this square inside. So each of these sides, from here to here, for example, would be 2, let's put this over here, 2 square root of 2, 2 square root of 2 over 4. Why? Because there are 4 sides, so we're trying to divide it by 4. And what does this equal? We can take this 2 and this 4 and we can simplify. So it would equal square root of 2 over 2. Got that? Because this would turn to 1 and this would turn into a 2. So we have square root of 2 over 2 is from here to here. Now let's focus on getting this to this right over here. So we have this line segment right here. This line segment has just been bisected by this radius. So it should be exactly half of this. And how do we find out what 1/2 of square root of 2 over 2 is? Let's just take that and multiply it by 1/2. What will we get? We would get square root of 2 over 4. So over here, we have square root of 2 over 4. Yay! Why is this important? This is important because let me shade this in for you, now have one side of my equation. A squared plus b squared equals c squared. This can be a squared, okay? So we have a squared plus b squared equals c squared. Why do I care about this? Because I'm trying to find this hypotenuse's length. Once I find this hypotenuse's length, what will I multiply it by? 8. I'll multiply it by 8 because we are looking to find the perimeter of the octagon that is inscribed inside of this circle. So we have square root of 2 over 4 is one of the sides. Which other side do we know? We don't know the hypotenuse. If we did, we wouldn't need to do anything here. So we're looking for this line segment now. Now this is a little bit trickier here, this line segment. And this takes a little bit of thought. So what do we know about this line segment? We know that it's actually a part of this line segment, which is the radius of the circle. And we know that the radius of the circle is 1/2. So I will start a new workspace over here. 1/2 1/2 is the total. Now, if the total is 1/2 and I subtract this length, I should get this length. Now, what is this length over here? This length is the same as this length. So we just subtract square root of 2 over 4. So 1/2 minus square root of 2 over 4 is the length of this line. Now we have the two lengths that we will be plugging into a squared plus b squared equals c squared, right? So we have square root of 2 over 4 in parentheses squared plus in parentheses 1/2 minus square root of 2 over 4 squared equals c squared. Yay, awesome. Now, if we can try to turn this into a little pretty problem, what I'm going to do is I'm going to turn it into an expression. So we have c squared. Let's find out what c equals. Remember that c is the hypotenuse of this little triangle that I shaded in. So to find out what c equals, we would have to square root both sides. And now we know what c equals, so this is what c is, right over here. And how many times do we need to multiply c to find the perimeter of that interior octagon, that inscribed octagon? We have to multiply it by 8. So if I bring the entire thing down here, I can start off with a beautiful big 8, and then I put a square root sign, and inside parentheses square root of 2 over 4 squared plus 1/2 minus square root of 2 over 4 close parentheses squared. Yay! This is the perimeter of the inscribed octagon. Got it? All right, let's go to the next page and solve this expression. All right, so what we did was we found the perimeter of this inscribed square, right? And the perimeter of the inscribed square was 2 square root of 2. So we had 2 square root of 2, right? Let's put a comma there. Then we created an octagon. And we found the perimeter of the octagon that would be inscribed there. Notice that I'm only drawing one side, but of course there would be other sides for that octagon. And the perimeter of that was 4 square root of 2 minus square root of 2. So what we're doing here is we would, of course, get a 16-sided shape by getting the center point of this line, and we would inscribe a 16-sided shape inside and find the perimeter of that, and continue on trying our best to find the perimeter of all of these shapes, and we would get closer and closer to the number 3.14159 to represent pi. Now, to represent pi, just remember we are finding here circumference. So what we're finding, all of these numbers would be circumference that we're finding. So we have diameter times pi equals circumference. So of course those numbers would then be, how do we find pi by itself? We'd have to divide both sides by d. It would have to be pi equals circumference over d. The reason why this is beautiful is because this is actually getting closer and closer to pi. Why? Because if you remember, we made sure that on the circle we were working with, the diameter equaled to 1. And that's why the radius was 1/2. So c over 1 would just equal c. So pi equals c in this example. All right, so I went ahead and rewrote our formula from before for the perimeter of the octagon that we are inscribing in that circle. And we are now going to start solving it. First and foremost, I like staying as organized as possible, so I'm going to draw an open-ended ray here, and I'm going to take this 8 times and this huge square root sign. I'm going to take them out. We're going to solve the interior of this, and then we will put them back in afterwards just for organizational purposes, so we don't have to keep writing this over and over, okay? So on the inside, we have square root of 2 over 4 squared plus 1/2 minus square root of 2 over 4 squared. Anything inside of these parentheses needs to be multiplied completely by itself again, because that exponent is outside of the parentheses. So let's go right down and let's start writing. Square root of 2 over 4 times square root of 2 over 4 plus 1/2 minus square root of 2 over 4 times 1/2 minus square root of 2 over 4. There we are. So for the first one, pretty easy. We only have a fraction times a fraction. So we multiply directly across numerator times numerator. Square root of 2 is, let's talk about this. What is the square root of 2? It is a number that when multiplied by itself will equal 2. And what is this square root of 2? The same thing. So since we have that same number times itself, it should equal 2. So we come down here and we write 2 over 4 times 4, 16. Bring down the plus sign, and then we go in here. Now, because we have 4 terms in here, we're going to use FOIL. First, outer, inner, and last. Got that? So first, 1/2 times 1/2. What does that equal? Under here, I will put a parenthesis just to keep things organized and so you can see what I'm doing. 1/2 times 1/2 will equal 1/4. Why? Because numerator times numerator is 1, and denominator times denominator is 4. Got that? Now next, we have outer. So 1/2 times square root of 2 over 4, except we've got this operator over here. So instead of minus, I'm going to use that as a negative sign. We make sure that we circle this entire term here with the operator in front of it. So it's actually 1/2 times negative square root of 2 over 4. So 1 times square root of 2. Down here, we're going to put the negative sign because a positive times a negative equals a negative. 1 times square root of 2 will just equal square root of 2 over, what is 2 times 4? 8. We have square root of 2 over 8. Great. Next, we have inner, square root of 2 over 4 with that negative sign in front of it. So we're going to do negative square root of 2 over 4 times 1/2. Well, we just did that, so let's just copy that down again. Negative square root of 2 over 8. And then finally, last, negative square root of 2 over 4 times negative square root of 2 over 4. What is a negative times a negative? It'll be a positive. And then square root of 2 times square root of 2 will just equal to 2. And 4 times 4 will equal to 16. Yay! Awesome. Now we have a bunch of terms. Do I really need these parentheses here? No, I don't. But I wanted to make sure you understood that from here to here came from there. Now I'm going to erase these because they are not necessary. And we have a bunch of terms here. Do we have any like terms? Like terms should have common denominators. We do, but honestly, I want to think about this as a like term too. Let's just manipulate it a little bit. How can we have 16 as the denominator? We can multiply by 4. But I think that the most advantageous thing to do would be, since these are 2's up here, to get everything over denominator of 8. Since I know it'll be more difficult to manipulate these in here. So 2 over 16, or 2/16 is equal to 1/8 plus 1/4 is equal to 2/8. I'm going to bring this over here. 2/16 is equal to 1/8 minus square root of 2 over 8 minus square root of 2 over 8. Awesome. These three, let's combine them. What do they equal? They equal to 1, 2, 3, 4/8 or 1/2 minus, now these are both over the exponent of 8, right? So what can we do with these if they're both over the exponent of 8? We can have them, as a matter of fact, let's make sure everyone doesn't get mixed up here. So let's keep this as 4/8 since it's all 8. So we have 4/8 minus square root of 2 over 8 minus square root of 2 over 8. How can we show this? We can actually show this by showing this denominator as just one denominator and all of these as the numerator. So we have 4 minus square root of 2 minus square root of 2 over 8. And I'm going to bring back this beautiful 8 and massive square root sign and put it back above them. Woo, awesome. So inside of here, what can we do? We have an 8 on the outside, and on the inside we have everything over 8. Can we just multiply through? Is it a possibility? Well, it is a possibility, but I want to look at the top over here. So we have 4 minus square root of 2 minus square root of 2 over 8. These individual terms can be manipulated. So we have this one, 4 over 8, and we have negative square root of 2, negative square root of 2, which is the same thing as negative 2 square root of 2. So 4 minus 2 square root of 2, or 2 times square root of 2 over 8. We're going directly down now, and now we can divide both of these by the same thing. So the 4 divided by 2 will turn into 2, and this 2 divided by 2 will turn into 1, or just not exist there. So we have square root of 2 over 4, because 8 divided by 2 is 4. And we put these all back under our big square root sign. So now let's talk about this 8. What was that 8? Do you remember why we were multiplying everything by 8? It was because it was an octagon. So we find one side, and we multiply it by 8, and we find the perimeter, correct? So I want to make sure that we make this distinction right now. This right here, everything except for that 8, is actually one side of the octagon. So that one side that we're looking at originally, which was right over, let's get our paper from before, right here, this one side, we now know to be square root of 2 minus square root of 2 over 4. And we're going to multiply it by 8 to find the perimeter. Got that? So to multiply it by 8, we're going to use, let's bring this all the way up here, some of the rules for roots. So 8 is the same thing as square root of 64. So we can actually say that the square root of 2 minus square root of 2 over 4, instead of being multiplied by 8, can be multiplied by the square root of 64. Now, because these are both these are both rooted, and we have a multiplication symbol in there, we can actually put the 64 inside. So we have 2 minus square root of 2 over 4 times 64. And for this, I'm actually going to show it as a fraction. So 64 as a fraction is 64 over 1. Great. Now that we have it this way, we know that we can multiply this across, right? All we have to do is multiply numerators and multiply denominators. But before we do that, we know that we can simplify. So 64 and 4 can be simplified here. We can divide both of them by 4. This will turn into 1, bringing it down so that there's no fraction here, just 2 minus square root of 2. Let's write that here. 2 minus square root of 2. And then the 64 divided by 4 would turn into 16. So we have times 16 on this side. Got that? And all of this is going to go underneath of the same big square root sign that we had from the beginning over there. All right, so now we have 2 minus square root of 2 times 16. So this times, can we just multiply it directly towards this 2? Can we multiply it towards this 2? Is there anything we can do here? Well, we actually don't have to worry about that. We remember what we did originally here. Well, we can undo this because we know that 2 minus square root of 2 times 16 inside of a square root sign is the same thing as square root of 2 minus square root of 2 times square root of 16. Why is that important? Because this is easy. Square root of 16 is 4. So let's bring that out to the front. That's 4 times 2 minus square root of 2. And we have the perimeter of the octagon. So we are now much closer to getting the perimeter of the circle. I'm going to put 4 square root of 2 minus square root of 2 as the perimeter of the octagon, but I want to make sure that I take this one side and I put that back into our work that we did earlier. So the one side that we had was the C right here. And I'm going to put a large square root symbol and 2 minus square root of 2 over 4, just to complete our work from before. Now we know all 3 of those sides for that triangle there. Got that?
So there you have it. What we're doing is creating a sequence where we have n term be the circumference of the shape inscribed inside of the circle, or the perimeter of that shape. And the formula that we would be using would be 2 to the n minus 1 square root of 2 minus square root of 2 plus square root of 2 plus square root of 2, and so on and so forth, for n minus 1 square roots. And that's a little bit complicated, but the process that we showed on paper and the geometry that we used to find pi is not as complicated as you might think, and is really visually pleasing. It's quite nice to take a look at it and go, oh, that's what I've been using. I've been using that number. The fact that people thousands of years ago could figure things like this out is just wonderful, and it shows that time is really not as important as we might think. We're not as advanced as we might think, because I'll tell you this, an everyday person now is not going to match up to a genius of 1000 BC. Really. So just put in the work and try to become as intelligent as you possibly can, and then always just lower your ego, because there were smarter people than you thousands of years ago. Way smarter than me, way smarter than some of the smartest people we have on earth today. Hopefully everyone just keeps working hard and we can catch up to how smart we used to be. Make sure to like, subscribe, and comment on anything that you would like to have explained, whether it's mathematics, English, science. We can do a little video for you. On top of that, also, info@sanitasacademy.com is where we accept emails. If you have any kids or any students that need tutoring, we do one-on-one, one-on-two, and one-on-threes during the COVID-19 crisis remotely. Talk to you guys soon. Be safe. Bye-bye.